Hello, everyone, and welcome to today's graph reading group.
Where we joined by Clément and Vignac once again, and we'll talk about discrete diffusion for graph generation.
Thank you. So thanks Hannes and Dominique for the invitation, and thank you all for being here. So I'm Clément. I'm a fourth-year PhD student at PFL working with Pascal Froissart. And today I will present DiGress, which is a model that we built for graph generation with discrete denoising diffusion models. And this is joint work with Igor and two master students, Antoine and Bohan, and of course our supervisors, Volkan and Pascal. So we are all from EPFL in Switzerland. So our goal is to generate graphs with categorical node and edge attributes potentially. So these are samples from our model. On the left, you can see two examples of graphs that don't have attributes. But if you want to generate molecules, you want to generate atom types, and you want to generate bond types, so you use discrete attributes. What I want to do first is explain what I believe that you need to know about diffusion models in general, not particularly relative to graphs. And then I'll explain our method, how we can improve over the vanilla models that you could think of, the results and things for the future. So let's start with denoising diffusion models. So as you probably know, if you want to build a denoising diffusion model, you have two components. You have the noise model. So you start from a clean input, X, and you add noise to it progressively. This is your noise model. It's modeled as a Markov process, so it factorizes with this equation. And it generates a diffusion trajectory that goes from a clean input to almost pure noise. The second component is the denoising network. So it takes as input a noisy input, and it tries to denoise it by one step. And you train the neural network to do it, so that once the network is trained, you can sample. And if you want to sample, you sample noise from a prior distribution, and you apply the network recursively. So the network is going to predict a distribution at previous time step that is supposed to be a bit less noisy. And you will sample from this distribution and iterate. And this way you can start from pure noise and get samples that you hope will be realistic. So if you train things this way, and that's what was done in the early diffusion models in 2015, you get samples like this on Cypher 10. So you can see that it learns something, but it doesn't really work well. And you know that now diffusion models, they achieve super remarkable results in terms of image quality, and particularly when you combine them with language models. I love this Sheeran example. So what was wrong in early diffusion models, and what was fixed in the more recent ones to get good samples like this? To understand this, let's look at the algorithms of modern diffusion models. They more or less look like this, with quite little variations in the end. So if we look at the training, what can we see? We sample a time step, we add noise until this time step. And then instead of predicting step t-1, usually we predict the clean input, X, directly. Or often we predict the noise that was added to the clean input, but it's kind of equivalent. When you want to sample, you start from noise as before. We apply recursively the denoising network as before, but now it predicts either the clean input or some noise. So we need to compute this integral on the right to get the distribution at time t-1, and we sample from this distribution. So what is different from training on trajectories? First, you can see that for training, we don't have to build trajectories. We just build ZT. And during training, we don't apply the network recursively. So this is very good in terms of computations, because this algorithm on the left is super easy to split on several GPUs, and you can massively parallelize it. This is a big advantage over normalizing flows, for example. On the right, you have sampling, and you can see that, okay, we don't predict time step t-1, we predict directly the clean input. So why do we do that? The problem with predicting time step t-1 is that if you train the network to predict zt-1, it's very noisy because zt-1 depends on x, the data that you sample, and depends on the trajectory of the noise. So you can think of a regression problem, for example, where you have a lot of label noise. So if you have a lot of label noise, it's eventually you should converge to the right solution, but it may take very long. If we can predict x directly, we remove this sampling of the trajectory. So we remove some stochasticity in the process. And in my opinion, that's why it's much easier to train. Okay, do we pay a price for this? Yes, we pay a price because if we want to be efficient, it means that we need to make extra assumptions. First, you saw that during training, we don't generate trajectories, we only generate ZT. So we want to be able to generate ZT as well at once. So we need a closed form solution for this. Then the integral to compute distribution at time step t-1, it should be tractable, of course, so that we can use X or the noise as a target of the denoising network. And finally, when you add more and more noise, you end up to, let's call it the limit distribution, where you kind of forgot about the input. And when you sample, you start from a prior distribution. So you want this limit distribution to be equal to the prior distribution so that you sample from the right thing. So you have these three properties that are important. And if you want to build an efficient diffusion model, you need to satisfy these three properties. Most people do it with Gaussian noise. It satisfies these three properties. But today we want to do discrete diffusion. I'll explain why later. So we'll check why these properties are satisfied in discrete case. So in the discrete case, you have like a discrete state space. So on the right, you have, for example, 3 atom types. And the noise model is a Markov process over this space. So you have a probability of jumping at each state, time step from state to state. And these probabilities are represented by transition matrices. So to go from time t-1 to t, you just multiply zt-1 by the transition matrix, and that's the distribution that you will sample from. Because it's a Markov process, if you want to do multiple time steps at once, you just have to do the product of the transition matrices. So this is good because if they are pre-computed, for example, then we can just go to time step t directly. There was this integral that we wanted to compute, but it's just Bayes rule in the end. And for the discrete state space, we can compute it as well. This is fine. And finally, the last property was that the limit distribution is something that you can sample from. And this depends on your noise model, of course, but the most common one is uniform transition. So the probability of jumping to another state is independent from the state. This is the formula written below. And of course, if you jump and jump, after some time, you converge to a uniform distribution.
Clément?
So, yes?
In the chat, we have someone asking what's the difference between the transition matrices at different time steps, but they're always the same, right?
Yeah, so if you look, for example, at uniform transition model, below you have QT. So it's similar to Gaussian diffusion. You can choose alpha t and beta t. Well, it needs to be to represent probabilities, of course. So it's the same formula, but varying coefficients. At the early time steps during sampling, you want to jump a lot. And at the end of the diffusion, when you kind of converge, you want more probability to remain in the same state.
Okay, but now this is for, no, okay. No, this is for whatever t we have a different transition matrix, so they're not always the same.
No, they're not always the same.
Yeah, but the difference between the different t's is basically there in the very bottom line.
Yes. This choice is arbitrary in the end. You could try to set them the same. I've not tried. Was there other questions?
No.
Okay. So let's move to graphs and to DiGress in particular. So the settings that we consider for now is unconditional generation. We have database of graphs with node attributes X and edge attributes E. And we want to generate new graphs that look like the graphs in the training set, but look like it's not so clear what it means. So for example, you have like antibiotics on the right, and we hope to generate new antibiotics. Of course, for now, it's just unconditional generation, and in most applications, you have some conditions that you want to impose, but at least you need to be able to do unconditional generation before moving on to more complex tasks. So I see it as a prerequisite. There are many reasons why you might want to generate graphs, but one important one is in drug discovery. And in the drug discovery process, it's a super long process, and we hope that this kind of models could help at the very beginning. Well, you have identified the target, and you want to find molecules that are active for this target. Small molecules, usually, that's called hits. And of course, chemists cannot test every possible molecule, so we'd like to have software that can suggest good molecules to test. So what are the challenges of graph generation?
Sorry, but correct me if I'm wrong, but this could be used at every step, even like for lead optimization, where instead of starting with a random noise graph, you can start with a graph that has properties that you like, but you want to optimize these properties. So it's not just like the same way that we've seen, for example, diffusion model in images, starting with a bad drawing and making a very high resolution drawing of that same thing. We can imagine such diffusion model being used in the same way for molecules as well.
That's a nice idea. Thank you. You're a better expert than me on this topic.
Yeah, of course, we can now make our generative model conditioned on something else, and we condition it on, I don't know, the drug likeness or whatever. Yeah, but I'm still let's talk about this molecule generation thing more later as well, when we get to some experiments.
Yeah. So graph generation is quite challenging, and I would say until like 2 years ago, we really struggled at it for two reasons. First, we inherit all the challenges of learning on graphs. So, okay, graphs have varying sizes, which you need to take into account, but okay, we know how to do it now. But also the standard graph networks have limited representation power, and this is another challenge, of course. And in addition to the challenges of learning on graphs, you have the challenges of generation. So depending on the architecture that you choose, for example, if you do graph generation, you might have to do graph matching, which is very problematic because it's costly and we have only approximate algorithms. You want to generate graphs that are sparse usually, and when you generate something, evaluation can be tricky. So we'll see that for graphs, we have quite a lot of tools, but that's the big challenges in general that we want to solve. So let's see what people have done. And if you attended the reading group last week, then you saw a great presentation. And if not, I recommend the YouTube video. So the only diffusion model for graphs that manages to generate attributes as well is this paper, score-based generative modelings of graph via a system of SDEs, and it's based on the continuous framework. So they add Gaussian noise to the adjacency matrix and to the features, and they use a graph attention network to do the denoising. This is very natural because, as I said before, most of the works on diffusion models are using Gaussian noise. And in terms of performance, it scaled really significantly better than, for example, what I had done in the past. They managed to generate good graphs on the database. You have 3 examples here. But still, the continuous diffusion is a bit problematic because Gaussian noise is not a super good model for an adjacency matrix. You'd like to respect the discrete structure of the adjacency matrix. And also you'd like to respect its sparsity, because if you add Gaussian noise, then it means that you have a fully connected graph, and that connectivity is not really defined, cycles are not really defined. And this can make it hard for the network to process the noisy graphs. What we will see experimentally is that indeed, if you go to discrete diffusion, then it's more efficient and you can scale it more. Okay, so let's get to DiGress, the method that we propose. So the algorithm is quite similar to what I presented before. You start from a clean graph. This is G. And you add noise to it to get to the graph GT. And then you train the denoising network to predict the clean graph from the noisy version. If you do that, then you get a probability distribution on the true graphs, and you train it with standard cross-entropy loss on every node and every edge. So what is important is that the noise is independent. It's added independently on every node and every edge, but it doesn't mean that it's generated independently, because of course the neural network takes the full graph as input. But the noise is independent, and this is important because it means that the state space that we consider, the ones that we use to build the transition matrices, is just the space of node types and the space of edge types. So it's small spaces, which is important to make the method efficient. So if we look at the algorithm on the right, we sample a graph, we sample a time step, we add noise to the graph by using the transition matrices, and we denoise it and just look at the cross-entropy loss on each node and the cross-entropy loss on each edge. Now, if we want to sample, we start from a prior distribution, and at every step, we will apply the denoising network that predicts a clean graph, and we combine this distribution with the conditional distribution GT-1 given GT and G to get to step T-1, similarly to before. So as you saw previously, if you want to do this, you need to be able to compute the integral over the inputs. But here, first, the inputs, this integral is just a product over nodes and edges. And second, this integral is just a sum, because you have a discrete state space, so it's the sum over the possible states. Yes, Dominique?
Yeah, could you go back to the previous slide where, yeah, this one where you sample noise, like you have the transition matrices Q that you described earlier, and how do they apply to the graph? Like when you apply the transition matrix Q on a certain graph, like what are the transformations that happen to that graph? Like how is it modified?
Okay, so it's the same transition matrix that is applied to each node and the same transition matrix that is applied to each edge, to each pair. So yes, I didn't mention it, but it's important. We do a prediction for every edge in the graph. So no edge, it's just one particular edge type, okay? So if you don't have particular attributes, you have two edge types. You have no edge or there is an edge. So you build a tensor. So X, for example, is n by A, the number of node types. And the transition matrices is A by A. So you apply the same thing simultaneously on every node and same thing simultaneously on every edge. Is that clear?
No, not really. So like when you try to predict if there's an, like, basically by you add noise to the existence of of an edge between nodes. That's one of the noise that is added. Like, is that right?
So let's say that we have a molecule. Okay.
Yeah.
So we have the atom types. So the atom types can change. This is the noise on the nodes.
Yeah. And do they change like from carbon to oxygen, or does it change from carbon to noisy carbon? Right. Like,
no,
what's the
noisy carbon does not exist. You're on a discrete space. So noisy carbon does not exist. Okay.
Okay. No, noisy carbon doesn't exist, and same as an edge with weight 0.5 also does not exist. So it's always
an edge with 0.5 does not exist. You can add an edge. It has to have an edge type, so you can go from no bond to triple bond, let's say.
Okay.
But you remain on this discrete space. So if I go a bit backwards, you had this Markov transition matrices. So that's the only state that exists. There is no
when you have so you basically have a probability that carbon would become oxygen, a probability that carbon becomes nitrogen, or that carbon stays itself, and that probability, like you don't apply the weights of the probability, you just sample one element of this probability. So for a specific atom, there's a 0.1 probability that the carbon becomes oxygen, and if you roll the dice 10 times, then the one of them will be changed into an oxygen, and the rest.
Okay.
Okay.
So maybe I can go now. Sorry.
It's just you have your categorical vector of in the beginning. It's a one hot vector of what atom type you have, and then you multiply it with this transition matrix.
Yeah.
You multiply it again and again and again, but instead of multiplying it again and again and again, you can also just multiply it with a single transition matrix that was, because we have this nice property as we have with Gaussians. Right?
Yes. And what matters is that you, from this noisy distribution that you have in the end, you sample from it. So your noisy state, it's in just one state.
Just one of the things that makes me wonder is that when you go, for example, from G prime from G to GT minus 1 here, both of them are valid molecular graphs. So I don't know, maybe that question will be answered later. You don't have to answer it now. But the question is that when you do these transitions, and again, when you go here to here, again, it's another valid molecular graph. So what tells the model that it has stopped, that like the fact that the cycle is broken is in noise, and not the fact that you just have a chain-like structure? Is it just trying to mimic the training distribution, like, or is there something else?
Well, it's really hard to tell what the model learns in the end, because the model just tries to reconstruct the input graphs. So it's really hard to tell. Maybe it will learn that there is no chain in the dataset, and that if there is a chain, then you should generate a ring somewhere. But it's not a prior. So
because in some sense, when you work, for example, with images, if you have an image of a cat and you add random noise, many times, you will never get the image of a dog or the image of a car. But in the case of molecular graphs, if you add noise many times, you can then become another graph that is also in the training data set, another graph that's also both valid and what you're looking for.
But
does that make sense?
Is it a bad thing? Because if we restrict the space so that good solutions are more dense, in a sense, I would say that it's a good thing.
But I mean, this is only the case because we're dealing with something discrete here, right? And we can also end up with many graphs that aren't very molecule-like and could not belong to, or where we will end up the overwhelming amount of times with a graph that is not similar to what we have in our data distribution.
Yeah, for example, you'll see examples on planar graphs, and it's quite constrained to be planar for a graph. So the noisy graphs most of the times are not planar.
Sure. I'll let you continue the presentation, and we'll keep this kind of discussion for later.
Okay. So one last thing that I want.
If I just may ask a short question related to what we were talking about. So in images, like you start from this Gaussian noise when you try to generate diffusion models. How do you sample from the noise distribution for generation? Like, how do you define how many? Like, how do you choose the number of nodes, the edges, and such things?
When you sample with DiGress?
Yeah.
So okay, first you need to pick the number of nodes. This does not change across diffusion. And the number of nodes it's sampled from the distribution of the training set. Okay, you just compute this distribution and you sample from it, yes. And then you start from a random graph, and this random graph will depend on your noise model. So if you start with uniform noise, you'll just sample uniformly as well. But this depends on your noise. The prior distribution that you sample from should be the limit distribution of your noise. The two are coupled.
Right. So in some sense, you also need to apply this uniform noise many times to generate the initial sample. So you sample the number of nodes, and then you do some sampling to get like some random edges.
Yeah, but you just sample once. I don't know. For example, let's say you use uniform transitions and you have 5 possible edge types. So you sample uniformly across these 5 edge types. You sample a matrix like this.
Okay.
So it's very fast. This sampling is efficient.
I just felt like sampling once might be biased towards like having less edges, because in that transition kernel, like the diagonal was kind of more high, like it had a higher probability than like adding an edge. Is that?
No, so if you go back to uniform transition, in the limit you add more and more noise, and the transition becomes uniform. So you don't have more weight on the diagonal.
Oh, I see. Okay, thank you.
But we'll see later that it's useful to push towards sparsity when you sample this noise.
Thank you.
Another question from Rodrigo.
Hi. Is this kernel only apply to like nearest neighbor nodes, or it's just on the completely initial nodes that you have?
No, it's on the complete. We compute all pairs and we make predictions for all pairs.
Okay, but could you generate more nodes? Could you include more nodes, or limiting factor is if you start with 10 nodes, the only thing that you could do is to change the type of node you are and the type of edge that describes?
We don't do that. It's probably possible, but we don't do that.
Last question. Could you incorporate, are you only right now describing atomic nodes, right? You don't have anything, like I think Hannes said that you don't have like CH3, OH2, like some sort of like conformers type of, not conformers, I forgot the word, but like multi-atoms that could be represented in a single node.
Yeah.
So right now you only have like atomistic nodes, right?
Yes, because we wanted to have a method that is like for general graphs and not only for molecules. But I think that for molecules you could have fragments. So you would have
that's the word.
More node types that are possible, but that should be an option.
Okay, thanks.
So one thing that I want to emphasize is that graph generation can be tricky. And in the past, I did graph generation with VAEs, and you had a graph, an encoder maps it to a vector, you try to decode it. Now you have a new graph, you want to reconstruct the first graph, you need to solve graph matching. And this was very tricky. The nice thing with diffusion model is that they solve this unconditional unsupervised problem, which is generates new samples that look like the training set. They solve it in a supervised manner. So here, graph generation is just a sequence of classification tasks where we try to predict the type of each node and the type of each edge. And these are tasks that we know how to do very well. Okay, let's move to the parameterization of the denoising network. So you have the architecture on the left. You start from a noisy graph. It has node features and edge features. You want to predict a clean graph with node features and edge features as well. But inside the network, we also allow for graph level features. Why? So we want to predict edge features. So it makes sense to have, we need to compute all pairs. So it makes sense to have an attention mechanism. And there are probably better experts than me of transformers here, but the way I see transformers is a stable way to implement attention so that you can stack a lot of layers and still manage to train them. So we use graph transformer layers. And we use these layers that have been proposed by Dwivedi and Bresson, but we extend them a bit so that they can take as input node features, edge features, and graph level features, and they output node features, edge features, and graph level features. So you can see at the bottom, like the attention mechanism, we incorporate the information from the edges to the unnormalized attention scores. Then we output the edge features and the new node features, and for the graph level features, we like pull the other features to update them. So honestly, we didn't spend that much time on this denoising network. We wanted a flexible architecture that looked reasonable. We designed this one, and we just did our experiments with this architecture. So when you generate graphs, you want to have permutation equivalence in general. When you work with graphs, the permutation equivalence, it's the mathematical way to reflect the fact that a graph can be represented by several adjacency matrices, and the adjacency matrix that you choose does not matter because you can reorder the nodes and get another one that represents the same graph. So our architecture, it's just the combination of permutation equivalent blocks. So it's permutation equivalent. Another thing that is important when you learn on graphs is that your loss, it depends on the task. It should be either permutation invariant or permutation equivalent. And here, to get the right property, what matters is that you compute the same loss on every node and you compute the same loss on every edge. So these cross entropy losses here, they do not depend on I and j. So we have this property as well, but these two properties are not always enough. They're enough for sampling, but not enough for computing likelihood. Because the likelihood of a graph, it's the sum of the likelihood of all the adjacency matrices that represent this graph. And of course, you don't want to do a sum over all permutations. But if you have exchangeability, which means that all the permutations are equally likely, then you don't have to compute this sum. So that's why we might want exchangeability. Okay, let's get to the first results. So this is a chain that we sample. We start from a random graph and we denoise it. So here you can see the different iterations until so the network gets to like a realistic graph. This is on QM9 with explicit divergence. So have we addressed the challenges of graphs that I mentioned before? Varying sizes, yes, because this is easy. As long as you use graph transformer network or graph neural network, you can have varying sizes. We have equivalence as we wanted. Sparsity, not really, because what you can see is that it takes time to generate a sparse graph. In the end, it's sparse, but it takes time. It takes many iterations. So this is something that we can improve probably. And I said that graph networks have a limited representation power. I think that many people have discussed it in this reading group. And this is something that for now we didn't really try to improve. So let's try to improve this now, getting something better than these first results. So for the noise model, I said that if you start from a uniform transition matrix, which is the most common choice because it's supernatural, then you have a problem with sparsity. It takes many iterations to get something sparse. Instead, you can change a bit the noise model so that you try to preserve the marginal distribution of the node types and the marginal distribution of the edge types at every step. And the way to do it is just instead of uniform transition, which means that the probability of jumping from I to J does not depend on J, we use what we call marginal transition. So the probability of jumping from I to J is proportional to the marginal distribution of J in the training set. So for example, most of the graphs have a high degree of sparsity. So when we sample, we will sample few edges as well. Hannes?
Yeah, just to be clear, right? You said, I think, that the transition matrix is different at each time step, but it's during the forward diffusion. But isn't it the same at each time step? And you just like if you are at time step t, the little t, and you want to get from 0 to little t, then the matrix to get to the little t is different with each t. But between each diffusion step, the transition matrices are the same, aren't they?
So they have the same formula? It's the formula here on the left?
No, what I'm saying is that, let me pull out my pen here. To go from here to here, I multiply with some q, let's call it. To go from here to here,
yes,
I multiply with the same q.
No, it's a q prime. It's another q.
Okay, I
Another
thought
q.
only if we go from here to here. But if we go from here to here, then we follow this formula, right?
No, this formula is for each q. Then if you go to do 2 steps, you need to do the product of the q's. And because these matrices are probability matrices, the product is nice. And it has the same form, but you just need to write alpha bar and beta bar. So for alpha and beta, we follow the cosine schedules that is used in many diffusion models. Yeah. So okay, then we have a mathematical justification of why you would want to preserve the marginal distribution of node types and edge types. But I think that in the end, the most clear is this picture. Is this figure where you can see that.
How did you find the mx bar and mx prime and me prime by like just setting the normal probability of each nodes in the dataset?
Yes. Yeah. Just computing it over the training set. Yeah.
Okay. Thank you.
So if you start from this, you keep something that is sparse in the process, and we believe that it helps the denoising network. And experimentally, you'll see that it does work better. Now, regarding the limited representation power of graph networks, of course, it's a super complex topic, so we don't have a perfect solution. But okay, we know that it's an important problem in practice because we know that graph networks tend to fail to detect substructures, simple substructures like cycles, or simply to know if the graph is connected. That's not so easy for a message passing network. So one solution is to use a more expressive network, and I worked on this topic in the past, and I think that many other people did, and we kind of all reached the same conclusions, which is that if you want to have an expressive network and keep permutation equivalence, usually you pay a lot in terms of computational cost. So we went for a simpler solution, which is imperfect, of course. And the idea is that if a neural network is incapable of computing some features, and you believe that these features are important, then you can compute them by hand and feed them to the network. So we had structural features like cycle counts. So node features like how many cycles does this node belong to, and graph level features like how many rings of this size are there in the graph. And we use spectral features like number of eigenvalues of 0, first non-zero eigenvalues, some eigenvectors. So these are things that are computed on the noisy graphs. And this is only possible because the noisy graphs are discrete. If you had a fully connected noisy graphs with some Gaussian weights, you would not manage to compute such things easily. So we compute these features and we give them to the network along with the noisy graph. Okay, so here are the final algorithms for DiGress. So I'll go very fast. For training, we sample a graph, we sample a time step, we add noise, we compute the structural features on the noisy graph. Then we give the noisy graph and these features to the denoising network that tries to predict the clean graph, and we train with cross entropy loss. For sampling, we start from a random graph. At each iteration, we compute the structural features, we predict the clean graph, we combine the distribution of the clean graph with the conditional distributions to get distribution at time step t-1, and we sample. So these are chains that we obtain in practice. These are the different datasets that we consider. So in the past, I worked with VAEs like 2 years ago, and I could only manage successfully graphs up to like 9 atoms. So I'm really happy with these results. So let's get to numbers now. And let's start with abstract graphs. So for these graphs, we don't have attributes. Here the colors are just for like illustrating. So we just want to compute if there is an edge or if there is no edge. No edge. Hannes?
No, first get through your numbers, then we get
okay. So how do we evaluate generation in general? It's a difficult topic. But for graphs, what we do typically is that we compare some properties of the graphs that we generate with some properties of a test set. So for example, we compare the degree distribution, we compare the clustering coefficient distribution, we compare the number of cycles, things like this. And then depending on the task, you might have more specialized metrics. And we train on 2 datasets, one of stochastic block model graphs and one of planar graphs. And the most interesting metric, in my opinion, is VUN, so valid, unique, and novel. So valid for SBM, it means that we run a statistical test, which asks, could this graph be drawn from the SBM model? If yes, it's a valid graph. And unique and novel, it means that it's not always a graph from the training set, and it's not always the same graphs, which would be 2 cases that are not interesting. And for planar graphs, we check if the generated graphs are planar. That's very simple.
Okay, so to clarify, with unique, we look at, is it already in the do you just always generate the same thing? With
yes.
Novel, we look, is it already in the training data? And with Valid, yes, we check, is it planar or is it from the stochastic block model?
So it's 2 different data sets that we test on. Okay, so yeah. That's for abstract graphs. Now let's go to molecules. So in the past, I worked on QM9 because it was small molecules, and almost everybody worked on QM9. And the method that I built like 2 years ago was set to graph VAE. And by like training maybe 8 hours, I would get to 60% validity. And now we are DiGress, we get 99% in 1 hour. So that's a very big improvement compared to what I managed to do in the past and what other people could do as well. So the model with implicit hydrogens, it has only up to 9 atoms, so it's very small molecules, and we can sample from it very well. You can see that, okay, we have a baseline, which is the same architecture, the same denoising network, but within a continuous framework, so with Gaussian noise. So our model Congress is very similar to GDSS, but it uses the graph network that we use for DiGress. So you can see that Congress manages to sample very well from QM9 as well, but it takes much longer to train. So since we get good results with implicit hydrogens, we can look at explicit hydrogens, which is a bit more difficult because we have bigger graphs. You can see that if you start from Congress, then going to to a discrete framework, you gain in validity. That you gain again in validity if you use marginal transitions rather than uniform transitions in order to preserve sparsity. And you improve again if you add the additional features that improve the network expressivity. So this was for QM9 that people mostly used in the past, but now that we managed to have good results, we can scale to larger data sets. One of them is Moses. So these are molecules from zinc. So let's say that it's small drug-like molecules. So they are still pretty small, but already more realistic. And one thing that is interesting with this data set is that the test set has separate scaffolds. So the scaffolds are the rings in molecules, and the split is done in such a way that in the test set, you have rings that are not present in the training set. And I think that we are the first method that works on Moses that does not either use a specialized representation like smiles or fragments, or that is autoregressive in the sense that it adds atoms one by one. And adding atoms one by one, it's difficult to compare to them because if you do that, you can check validity at every step, and if you're invalid, then you can resample. So it's kind of an unfair advantage over methods that cannot compare, that cannot measure validity during sampling. And what we observe is that, okay, smiles seem to be much better. So it's a very efficient representation, but it's super specific to molecules, and it has some limitations that maybe in the future we'll manage to overcome. But that our model is like on par with GraphInvent, except on the validity metric for the reasons that I mentioned. So we managed to bridge the gap with autoregressive methods, and that's nice because there was a big gap in the past. One metric that is interesting is the one on the very right, which measures the proportion of molecules that you generate that have a scaffold in the test set that is not present in the training set. So in a sense, it measures the molecules that are truly novel, that are not a minor modification from an existing molecule, because they have a new ring. And what you can see is that the smiles-based methods, they have a low score for this. So it means that they have quite low novelty. And DiGress has a better score at this. So we believe that this is very promising for the future. Finally, we went to an even bigger data set to see the limits of the model. So GuacaMol, it's also drug-sized molecule, but it's like larger molecules on average. And again, you can see that smiles perform better currently because they incorporate more knowledge about chemistry. But that our method, it's let's say the first one-shot one to achieve correct results. So you can look at the metric on the right. That's the most interesting, I would say, because it measures the similarity of the graphs in the test set and similarity of the graphs that you generate. And we can see that when you scale to this size, then the continuous model does not work anymore. So in terms of scalability, like the discrete framework really helps. So let's summarize this. We do unconditional generation, and DiGress solves it by solving a sequence of classification tasks on every node and every edge. Each task individually is something relatively simple conceptually, and we solve a sequence of them to do generation. That in general, you've seen the results of GDSS. They were already much better than previous results. So diffusion model for graphs really work well. But discrete diffusion helps scaling even better and training faster. So it's really a useful framework when you want to train on discrete data. And that, okay, we still have a main limitation, I would say, with this model, which is that we make predictions for every pair. So we have this n-square complexity that we cannot avoid. And it means that with this method, you will not manage to generate social networks. Okay, you have a limit in the number of nodes that you can handle. Let's get quickly to things for the future and things that we've started to do. The first one is conditional generation, because as I said before, most tasks require conditional generation. And for this, we propose a discrete guidance procedure. So here we work on molecules on QM9, and we want to condition the generation on some graph level properties. For example, it could be solubility or something like this. And I'll go quite quickly. The basic idea of guidance is that you use an unconditional model, but in addition to that, you train a regressor to predict the properties. So the regressor takes as input a noisy graph and tries to predict the property of the clean graph. And when you sample, you use the regressor to push the sampling towards the properties that you want. So in practice, if you want to write this, you assume this model on the right. This graphical models means that if you know the clean graph G, it's used like the conditioning value Y gives you no information about the noisy graphs. So this is normal because if you know the clean graph G, then you can compute the conditional information. And if you have this, then using this graphical model, you have this formula for sampling. So when you want to sample t-1 given zt and your conditioning property, you have the unconditional model. And then you have this term, which is the probability of y given gt-1. But if you want to compute this, you need to know the value for any possible gt-1. So you cannot sample from it. So what we do is that we use a first order approximation. So instead of the value at gt-1, we use the gradient of the value at gt. So that's the main idea of guidance. In practice, what do we have to change in the model to do this? So we have the unconditional model. Then on the noisy graph, we also estimate the property y hat. And we compute a distribution, which is an estimate of the probability of y hat given gt-1 using the gradient of the regressor. And we use this property to push the model towards the right property. So how do we evaluate this in practice for the experiments? So we did it on QM9. So we have some properties that we condition on. We have the dipole moment mu and the HOMO, its highest occupied molecular orbit, two properties that are computed in QM9. And so we generate graphs conditioned on these properties. And then when we have new graphs, we need to estimate their properties as well. So we use a software called Cypher for this. And we measure the distance between our target property and the properties that we obtain. And what we observe here is that guidance helps. It reduces the distance between the obtained property and the target. But still, there is quite a lot of room for improvement. So there is more for the future on conditional generation. One other thing that is very easy to do with this model is condition on an existing subgraph. This for molecule, it's called molecular scaffold extension. So here you can see molecules that are conditioned on a substructure. And you can see that it fails quite often. It doesn't look like very realistic molecules. And a similar thing was observed for images, in fact, in a paper called Repaint. And in this paper, they found a good solution based on resampling. So probably, if you want to do good subgraph extension, you need to use this mechanism as well. And I believe that it would work. other things that we've not done so far. So today I've only showed you how to generate graphs with discrete node types and discrete edge types, but maybe you have continuous properties as well. If you want to implement such a model, it's not super difficult, it's just a bit of work, because you need to define the noise separately for the continuous part and the discrete part. But it's just like an implementation problem. It's not really difficult, just some work. So there are probably many settings where we want both continuous and discrete generation. As you've seen, there is room for improvements on conditional generation. On molecules, people probably want to do property optimization, for example, for heat to lead optimization, as Dominique was saying. We probably want to do fine-tuning to be able to train a big unconditional model and specialize it on some small data sets. And the big question for the future, which is, in my opinion, much more tricky, is there a way to have a generative model that is permutation equivalent, but does not have the n-square complexity? And I believe that this is very difficult, because if you have permutation equivalence, you have no way to know in advance if a specific pair Yj exists or not. So probably you need to compute all pairs and to make predictions for all pairs. So this seems to be a tricky problem. So that's all that I wanted to show you. So I'll take questions now. Thank you.
All right, many questions, I think. But thank you for the nice presentation and explaining everything to us and the nice paper. Then first of all, can you lose a few more words on the condition, or like on your marginal, not having just a uniform distribution as the stationary distribution?
Okay.
How does it work? I didn't really get it.
Okay, let's get back to it. So first, one thing that I want to say is that if you have expert knowledge on your task, it's probably in the noise model that you can incorporate it. For example, for molecules, maybe you don't want to be able to go from single bonds to triple bonds, but you have to go to double bonds first, things like this. So in general, here you can work and adapt your method. Then if you don't really know what to do, you can do this, which is use the marginal distribution. So let's say that in the graph, you have a sparsity degree of 80%. So 80% of the pairs correspond to no edge. And 10% of the pairs correspond to edges of type A. In the marginal transitions that we propose, we choose it in such a way that the probability of jumping from any state to no edge is 8 times bigger than the probability of jumping to any state to type A. Okay, that's the main idea. So that's if you add more and more noise, you will end up with 80% of the pairs that are in the state no edge, and that's the distribution that you sample from, like your prior distribution.
All right, ideal. Ahmed?
Hello.
Hello.
So while training the model, you were sampling a timestamp t and calculating the graph at that timestamp and using the denoising transformer to predict the clean graph. So is it necessary to sample the timestamp, or you can just take a single graph and predict every step of it and just predict the clean graph and update the graph transformer thing? That's one question.
Instead of
is it necessary to
step,
yeah.
Okay, so I've tried that in fact, and it didn't really work. But instead of doing one step backward, which is slow, that's a limitation, you can do several steps. So I don't think that people have done it for discrete diffusion, but there are a ton of works for with Gaussian noise that do this. And actually the formulas would be the same. So it should be possible to implement it as well. So you wouldn't go directly to the clean graph. This does not work super well, I checked. But if you want, you can do several steps backwards at once. You need to adapt a bit the formulas, but it's not very difficult. You can look probably a paper by Stefano Herman 21. Many papers did it, but you
Okay.
have to look at Gaussian diffusion for this.
Okay. And about the sampling the number of nodes from the dataset, it's for the so it's done because to give equal importance for all different sizes of graphs in the dataset, right?
So
You also sample the number of nodes.
Yes, you want to generate the distribution that you want to generate. It should have probably the distribution of number of nodes should be the same as in your training set. This makes sense.
Okay.
Honestly, we did it because almost all graph generation papers work this way. And nobody really found strong evidence for now that it's very important to do something else. So that's just the simplest. And it's not so clear that it's not good enough.
Like
But
if you
it's
just
probably
fix the number of nodes as they are in the initial training data set, should it also work? Like I have.
Yes.
Okay.
And if you want to generate 200 nodes and only 200 nodes, you set it to 200 and you'll see what it will generate. But,
yeah, understood.
You can choose it. Dominique?
Thanks, Clément, for the awesome paper. Like there's a lot of great things and great results that we can see here. And yeah, it's good to see like the last two presentations on graph generation with diffusion model. So I really hope like this is one of the first stepping stone to get to what to what DALI is able to do, or what stable diffusion is able to do. However, like I have many questions or comments about like the sampling method and how you generate noise in graphs that for me like could be one of the biggest points of improvements in the paper. And let me explain why. So so first, like I want to let's go to very chemistry perspective, and then we'll jump into the graph perspective. When you have an atom, like a probability of transition, for example, for carbon to any other atom, like let's say carbon to nitrogen versus carbon to chlorine versus let's say hydrogen to chlorine. In your case right now, they all have like, for example, the same probability, right, of transitioning, or no?
Yeah. Like for example, carbons are more frequent, so probably you will transition more often to carbons. But yes,
yeah,
we don't add a lot of prior knowledge.
So one thing that I think could be very helpful in case of molecular graph would be maybe to allow a transition to only happen like at every step that you add noise. Transition can only happen one step on the periodic table, like either left, right, up, or down on the periodic table, so that that way, like when you add because the idea is like to not add noise one time, right? If you wanted to add noise one time, then what you do makes a lot of sense. But since the goal is to have noise that increases slowly, and that from one noising step it's easy to denoise, and the other two noising step is a bit harder, and so on, then it would make sense that the first that for every noise step that you add, the properties are more preserved, and they would be more preserved if only one step on the periodic table is made. Does that make sense?
Yes, absolutely. In this paper, we wanted to make a general method for graphs that is not too molecule specific. One thing that we thought about is try to compute energies and to make the transition proportional to like energy changes. We're not sure exactly how to compute it. What you propose is another option. I believe that in both cases, it's very pertinent for molecules, and that your expert knowledge, it should be first in the noise model, because that's a place where it will probably really help, and you don't really need to change the framework, just the transition matrices that you need to define in a more clever way.
Yeah, in some sense, for example, when you add Gaussian noise on images, you can change a very red pixel to a very blue pixel in one step, but it is not desired because like you add the noise step by step. So if you want a transition from very red to very blue, it will require many steps of adding noise for that to happen. But something else that I want to say, like regarding general graphs, is again the fact that like since noise must be small, I think. Well, I think if you go back on the other slide where we were, it would be easier to visualize it on molecular graph, even though like we're talking about general graphs. Is that, for example, this molecule here, which is one step before the final output, is kind of a nonsense molecule because many things are connected at random positions. And this is because like with the transition matrix, things like any edge between any pair of atoms has the same probability of being added or removed. And I think this is the case, right?
So this one that you see here, it's 100 steps before the final output.
Okay, it's 100 steps before the final output.
So
okay, that makes
when
sense.
you design the schedule, here we use the cosine schedule because it was simple and in the end it worked. But you can also think differently and say, I want, for example, to have one edit in my graph on average per time step. So it's still discrete transitions, right? But you can say that you want your graph to change little at each step, and this is a very reasonable assumption.
Yeah, so my comment is like, even if you want the graph to change a little, there are things that a single change that can have major impact on the graph structure. For example, like if we consider like a community graph where you have a large community here and another large community here, and they are connected only by one bond, then destroying this simple bond here will change a lot the graph. And again, like adding a connectivity between like this one here and this one here and having them connected will also change a lot the graph. This is very easy to see also like in a molecule where you have like a molecule here, and adding this and destroying this will change a lot the molecular graph. So what I was wondering is like, shouldn't the probability of each node and edge being changed also depends on like where they are in the graph, and shouldn't like the probability of an edge being created between two neighboring nodes be much more likely than between two nodes that are very far, so that you can have nodes that are very far being connected after applying the noise many times in sequence, but you will never have two nodes that are extremely far being connected on the first occurrence of the noising. So what is your opinion on that?
That's maybe possible, but for sure that's not easy. For example, what's the limit distribution if you apply this process repeatedly? That's not so clear. Then do you use a network to predict this? It may be possible. When I started this project, what I believed at first is that when we use discrete diffusion, we cannot really control the scale of the changes because it's discrete. So you cannot make infinitesimal changes like in the Gaussian model. So I thought that it would take some work to make the discrete framework work better. And actually, when we implemented the model from the very beginning, it worked better than the Gaussian framework. So this problem of controlling the scale of the changes, it's less important than I thought it would be. then is it still a problem and can we improve it? It's still very interesting questions that I've not really solved.
Yeah, so I do agree that like I'm also surprised by the fact that you do not control the intensity of the changes and you're still able to diffuse back. But I would say, for example, when your goal is to do molecular optimization or yeah, if you want to do molecular optimization or if you want to do lead optimization in general, you have a property, constraint optimization is the word that I was looking for. So either lead optimization or constraint optimization, and you start with something that works well. It'd be nice if like the model learns more like the local changes that are important, because you'll never have like, so what I drew here on the right, it's never something that a chemist would do in lead optimization phase, right? But having like smaller changes happening, like having smaller changes happening in that region and another small change happening in that region looks more like what would likely happen. And yeah, so you said controlling the scale of the changes is something that is difficult, but I think that just constraining changes to have much higher probability with close nodes than with far away nodes is in some sense constraining the intensity of the change. This is different than what is like, I mean, because it's different than what's done in images, because on images you constrain the intensity simply by multiplying the Gaussian noise by a small factor. In discrete graphs, you cannot do that, but you can kind of guess what kind of changes are more destructive just by using this kind of constraint on the distance.
Yes, I've not tried it, so I cannot really tell you. It sounds completely reasonable. At the same time, maybe the denoising network manages to learn well changes that are important and the ones that are not. I cannot really tell. I can tell you that discrete diffusion, it's used mostly for text. And for text, what you can do is constrain the diffusion to change from a word to a neighboring word in a semantic space, so that you don't go too far too fast. But this, for molecules, it would, for example, means, as you said, not changing the atom type arbitrarily. Then this spatial proximity, it looks more difficult to me, but maybe it will improve later.
Yeah. Anyways, it'd be great to see like how changing the sampling could help, because I really like the work that you've done, and I think it's really amazing to see it work. And I think bigger than the n-squared complexity is the sampling method, but that's just my opinion, no proof to back it up. So thanks again for presenting today. And I'll let Francesco continue with his question.
Hello, Francesco.
Hi, can you hear me?
Yes.
Okay. So thank you for the very nice work. So I have quite a few questions, but maybe, so if I understand correctly, you use the one-hot encoding all along the generation process. But do you think it's possible to use like probability of the state, or this will destroy the transition?
Okay, this is something completely different. So let's go to the algorithms maybe. Yes, at the bottom. So we compute probabilities at every step, but then we don't diffuse the probabilities. We sample from the probabilities to get a discrete value, and we repeat the process. You can have diffusion models that does not operate on the space, on the discrete space, but that operates on the space of probabilities. And then it would be, in a sense, a continuous model, but over the space of probabilities. it's something quite different, and it's much closer to continuous diffusion in the end. But that's an option. I think that you can have a look at the paper about multinomial diffusion by Emil Uchbaum in 2021, because that's I think that they do something similar. I cannot hear you anymore.
Sorry. What do you think will happen to your model if you go in that direction? Of course, you lose the discrete property.
Yes. If you look at the GGSS paper, for example, they do continuous diffusion and thresholding to recover the graphs, this kind of thing. I think that they manipulate continuous tensors, but at every stage you can map this to a probability tensor. So I think that it would be very, very close to their method. So what we found is that discrete seems to scale better, but yeah, I cannot really tell you if you operate directly over the space of probabilities. I cannot tell you exactly what it changes.
Okay, thank you. Sorry, and why do you split in test and training if you then just check the generated model? Do you also check if any generated graph is in the test set?
We don't check this. But mostly what we want is to make sure that we don't just replicate the training set. So we compare the distributions with the test sets, but it's something that we could check, but we don't check it. I've not insisted on it, but one key drawback of diffusion models, especially those which use naive sampling, as we do. We don't use particular tricks to speed up sampling. Sampling is quite slow, so it's not that easy to generate 1 million molecules to check if they are in the test set or not. And since the molecular space is so big, for example, we would need to generate really a huge number of molecules to check this property.
Last question is, what validity do you check, for example, in the Moses dataset? Is it the bound or?
For the molecules? Yes.
Yes.
Yes, validity is just like that atoms have the right valency. So it's a very basic metric. It's not really sufficient to give you good information. That's why these two data sets, Moses and GuacaMol, they give you much better information. What can I explain? For example, the filters metric here. So they used a set of filters to generate the training set. And you check that the generated molecules pass the same filters, like are they soluble in water, some properties that they have. Do they have the right weight? So I think that this one is, for example, a much better metric than only validity.
Thank you.
Andy?
Hi. So this is a very nice talk. So I have maybe a silly question. Can you go to the previous slide? So I'm wondering, like, so what I'm going to do is once I have a question, like once I have this model, so can I measure the likelihood of each, let's say, sample in each graph sample in my training data set? So I see you can compute like this negative log likelihood, right? In the first table.
Yes.
Yeah. Sorry.
Yeah,
go ahead.
Computation. Yes, we can do the computation. I didn't really mention it, but yes, we can measure it.
So there is a closed form, like I mean, mathematically closed form to compute that.
Yes, because it's over a discrete space. It's really not difficult.
Okay, that's good to know. And for the others, like those continuous one, you cannot compute that, if I understand correctly, or we can also can. So for other like for other models. So for other like you also, I think you also have like continuous graph, right? So it's a CONG. So for that one, I see you didn't like fill in
Yes.
that column. That entry, is that because like it cannot compute like the likelihood?
No, we can compute it. I just think that there is a bug somewhere in our code because the results are strange, but we can do the computation.
I see. Okay.
Yeah.
And another question is, if I don't have let's say a graph from my training data set, but my I just arbitrarily give you a graph, we can also compute that, right? So
Yes.
that's the likelihood. Okay.
Yeah.
Got it. Yeah, thank you. Yeah, I just have this question.
You're welcome. Any other question? I didn't check the chat. Is there any questions in the chat?
Let's maybe consider, how much do you weight the edge loss versus the node loss in your training?
So yeah, we give more importance to the edges because what we found out in a previous project is that if you know the edges, it means that, especially for molecules, it means that you know the valency, and the atom type is quite easy to guess. So that's why we have the cross entropy loss with the lambda. I think we choose 5 in practice. So we give more importance to the edges.
So have you considered also using a different noise schedules for the noise on the edges and the noise on the atoms? Because as you just said, figuring out the atoms is pretty easy from the bond structure.
Yeah, that sounds like a good idea, but we've not tried.
Yeah, maybe it makes sense to first decide what your bonds should be, and then you decide what your atoms should be. All right, another question.
Hi, Clément. Thank you for the talk. I think you mentioned that the dimension of either the node or the edge features impact the performance of your model. Like what's the maximum size of the, I don't know, the edge dimension that you've tried?
The number of features that?
No, sorry, the dimension of features. So here that would be like, I guess.
The number of nodes?
No, so like for example, like the feature for each node would be like the atom type. So that would be, I guess, like 1 dimension with like cardinal, I don't know, like 4. So I don't know if you, yeah.
We have 1 single dimension, if you say things this way.
Okay.
Like molecules have 1 atom type and 1 edge type.
Yeah.
I've thought about it. You could have more. Just in terms of implementation, it's a bit of work.
Okay.
But yeah. So I don't think there is any fundamental restriction, but we have only 1, in fact. Nodes have 1 feature and edges have 1 feature as well.
Okay, thanks.
Any other question?
Yeah, well, there we go.
Yes, so I forgot actually it was before. Would it be possible to model, and would it make sense to model the coordinate of the atoms as a continuous variable?
Yes, absolutely. This is in the mixed continuous discrete that I talked about in the end. If you have coordinates in particular, you probably want like E3 equivalence in addition to that, equivalent to rotations. So you need to change the model accordingly. I think that it would be very useful because there is a lot of evidence that for learning on graphs, 3D coordinates help. So maybe they help as well to generate graphs. So I've not talked too much about it, but there are many models that generate molecules in 3D. And these models currently, they don't generate the bonds. They only generate the coordinates and recover the bonds from the distances. And combining these models with DiGress would be a way to have this end-to-end. So you need to change the noise, of course, and to change the neural network as well. I believe that it would work better, that it's a promising direction.
Thank you.
Okay, so we now know how to do discrete diffusion for graph generation, but Clément also told us about many follow-up ideas like conditional generation, building in some scaffolds or some motifs in the beginning and then generating from that. So maybe you can go ahead and do that. If you do, let me know. I will be interested. And if you want to join future reading group sessions, all the information is in the description. See you.